Criteria of optimality. The most important and widely used method for designing FIR filters is to use a computer program to optimize the impulse response or BK, K from 0 up to N minus 1. For a filter with a limited response, y of n is equal to summation k from 0 up to N minus 1 bk times x of n minus k. A description of the appropriate filter in the frequency domain is given to the program, and then an error criterion is sought to be minimized. The program always tries to have a symmetric impulse response to ensure phase linearity. The optimized quantity is often the maximum deviation from the desired domain response. For filters of type FIR, this provides a design where peak deviations from the desired response, that is ripples, are all the same size. This design method is based on minimizing equal deviation errors for ripples, which is known as equi-ripple design. Now, the next topic. Design details of FIR filters using optimal method. An optimal filter is one in which, according to the Chebyshev approximation theory, the approximation error has at least m plus 1 over 2 plus 1 change of sign with the same amplitude on the desired ranges. Therefore, such filters are also called equi-ripple. The optimal method tries to minimize the maximum error. Another name for this method is the minimax design or minimax criteria. Its purpose is to change the coefficients of the impulse response so that an optimal approximation of the desired frequency response is obtained. Nonlinear methods can also be employed. However, the goal here is to use linear techniques, although they may be slower to run compared to nonlinear methods. The critical frequencies of the desired frequency can be precisely determined. Suppose we want to design a low-pass filter with a linear phase and with the following characteristics: amplitude deviation in the passband plus minus delta p, amplitude deviation in the stopband plus minus delta s, passband edge frequency fp, stopband edge frequency fs, of course for low-pass filter is greater than fp. Considering 4 types of symmetry in the FIR filter, we will have FIR filter with the symmetry of the first type. H1 will be equal to e to the power of minus j half m times omega times hr of omega, where hr of omega is equal to bl plus 2 summation k from 0 up to L minus 1 bk times cosine of L minus k times omega. Okay, we had definitions earlier in the previous lecture notes. FIR type 2 symmetry, I will leave it for you in order to shorten the duration of the recording, because we have explained it earlier. The third type as well, and the fourth type. Okay, now the weighted error function is defined as follows: error of e to the power of j omega will be equal to weight w, capital W, weight of omega, a weighting factor, a weighting function, times hr of omega minus h desired of omega, where the desired frequency response is represented by hd of omega and the weighting function is shown by W of omega. The weighting function is chosen by the designer and indicates the relative range of error at different distances. The sample form of the desired frequency response is as follows. H desired is 1 plus minus delta P for passband and 0 plus delta S for a stop band. The weighting function can be in the following form. W is 1 for passband, 0 for transition region, and delta P over delta S for stop band. Or maybe of this form. Delta S over delta P for passband, 0 for transition region, 1 for stop band. Okay. The coefficients of BK are unknown variables that must be found so that the maximum absolute value of the error be minimized in the interval from 0 up to pi. If the answers are found, the frequency response will have equiripple behavior. Two researchers named Parks and McClellan were the first to solve the above problem using an algorithm called Remez exchange. The corresponding algorithm is explained below. A filter with a linear phase that minimizes the maximum weighted Chebyshev error is defined as, here you see the details. Okay? I don't read it out. And again, I will skip the reading. You see every details here. Okay. The periodicity theorem states that absorb E reaches its maximum value at least at R being equal to S plus 2. Also, the weighted error function has a change of sign at least at the same R being equal to S plus 2 points. Okay? The maximum and minimum points in the number of R appear as omega 1 up to omega R in ascending order. Meanwhile, error of omega will be C times minus 1 to the power of I, norm of E of omega, where C is equal to plus 1 or minus 1. The following equation can be used to approximate the filter degree. Okay, here you see an approximation to find the degree. We will use it inside Python program. Okay, delta F has been also defined as the difference between a stop band and a cutoff or passband frequencies. Now, FIR filter design using optimization method. The Parks-McClellan FIR algorithm tries to equalize and minimize the ripples for a given frequency profile and assumed filter degree. If the degree of the filter is small, the program may not be able to find an equiripple solution. On the other hand, if the given filter degree is too large, the result will be a filter with uniform ripples that will exceed the specified requirements. So, the design steps are: the first step includes determining the frequency ranges, the average level of gain, usually with linear units for each frequency range, and the relative weighting of the ripple sizes for each of the frequency ranges. The last characteristic allows filters to be designed with different sizes of ripple in different frequency ranges. The second step is to estimate the filter degree. Simple equations are available that provide a first estimate of the degree required for the filter. It can be changed in successive iterations to find the minimum required degree. Then, an optimization program is executed to calculate the filter. The Remez command is used for the first two steps above, and the Remez function is used to design the filter coefficients. Of course, in newer version of MATLAB, you need to use PM-ORT instead of Remez-ORT, and for this part, Remez is substituted by PM, FIRPM in MATLAB. Okay? It is necessary to check the result, usually by plotting the domain response to ensure that the program has found an equi-repel solution to satisfy the requirements. The freq command is used for this purpose, or any method you are familiar with it. If the design requirements are not estimated, for example, there is no solution with the same wave amplitude, the value of the estimated degree of the filter should be slightly, not sharply, slightly increased, and the Remez command should be executed with the new degree of the filter, and the result should be checked again. Iterative procedure. This repetitive procedure contains until an acceptable result is obtained. It's a technique. It's a programming style. Since it is difficult to write the code in Python for Remez, or of course I have written it for myself, but you don't need it. Okay? Again, since it's difficult to write the code in Python for Remez or to estimate the filter degree, those interested are requested to use the Remez command in MATLAB for this purpose. Remez or PM-ORT. We have promised you to write codes and programs from scratch in a very simple style. So if you want to write Remez in Python, it's not recommended, unless you are pretty familiar with coding in Python. Anyhow, example 6.6. For an FIR low-pass filter using Remez exchange, write a Python code for the specification as follows. Fs 8 kHz, keeping the same examples for newer discussion as well. 8 kHz for sampling frequency, Fp 2 kHz, delta F 800, attenuation 40 dB, and passband repel 0.1 dB. We didn't mention it for Windows method. Okay, but here it's a parameter as input to the program. Okay, now we'll go to PyCharm and run the program. Okay, let's start from the figure 1. Figure 1. Here you see a low pass. Okay, passband, stop band computed and plotted as green sign and red sign, and blue stands for the amplitude of the frequency response. This is figure 1. Figure 2, frequency response in dB. You see here minus 40 dB attenuation in stop band, and this is low pass. And here the third figure shows impulse response in time domain as well. Okay, here you see the results: estimated degree 90, passband repel and stop band attenuation, and computed Fc and Fs, and computed delta F. Now going back to lecture note. Here you see the details of the coding. Okay. Declaration of the parameters. Uh, Computing stop band frequency FC plus delta F, delta P, and delta S being converted back to normal numbers, not in dB. N, estimated degree Fs, Fc, Fs, delta P, delta S using the equation we just showed in the lecture note and using it later, initializing the variables, okay, and using the command remez, signal.remez, n plus 1, f vector, attenuation, deviation, and stop band. Okay, so we need three important vectors. Here you see f vector contains 0, fc, fs, and half fs. We have these key parameters for low pass: 0, fc, fs, 0.5 times fs. What about attenuation? For low pass, pass, and prevent. So 1, 0. Okay? What about deviation? 1 over delta p, 1 over delta s will be passed inside the function. In MATLAB, here you will use delta p and delta s directly, but here there are some differences from MATLAB environment and Python environment. Anyhow, remember these. We will later design high pass as well. So high pass will be, can you say it? Starting from 0, then having fs, then fc, then last parameter the same. What about attenuation for high pass? Will be 0, the next one, 1. And here delta s at first and then delta p. It will be high pass. Very simple. Okay. Again, similar coding for computing the parameters and plotting. Just fast scrolling. Here we won't run it for high pass because we have no time for recording. You see here, this time, what you see here, fpass has been declared 2 kHz. So the details of the program, estimation for degree here, the same coding as we showed in lecture note in details, theory. Okay. Estimated degree and printing it. Here you see 0, fs, fc. The fourth parameter is the same as low pass. But the second and third parameters differ from low pass. And of course, attenuation 0, 1, and deviation, the first deviation 1 over delta s because stop band is in lower frequencies, and then pass band. Okay. But I will run the program for band pass filter. Okay. For an FIR bandpass filter using Remez Exchange, write a Python code for the specification as follows: Fs 8 kHz, Fp 2 and 3 kHz, having two passband frequencies declared, delta F 400 Hz, delta S 40 dB, and ripple for passband 0.1 dB. Now running the program inside Python. Okay, let's have a look to figures. Band pass filter, two pass bands in green color, they have been computed and shown in figure, and two stop band frequencies. Pass band having two stop band up to fs over 2, 4 kHz. This is figure 1. And this is figure 2 using a logarithm. Here you see about 40 dB attenuation. Okay. And the third plot is related to impulse response, which is not important for us right now. Estimated degree is 37, and the rest of the parameters, I won't read them up. Okay. Now, having a deep look into the coding and showing the key parameters. Right. Of course, all parts of the program should be important for us to get the results. Anyhow, fs1 and fs2, how they are computed, delta p, delta s, the same manner, estimate degree. Now, you see here, frequency vector contains 6 parameters: 0, fs1, fc1, fc2, fs2, and the last one, half fs. Okay? What about attenuation vector? Don't pass so 0, let it pass so 1, and the last one, 0. What about deviation? 1 over delta S, 1 over delta P, and 1 over delta S. Okay, but the rest of the coding is similar. Again, using Remez in the similar style. Okay. Now, band stop filter without running inside Python, but showing the details. For an FIR band stop filter using Remez Exchange, write a Python code for the specification as follows. Fs 8 kHz, this time Fs 2 and 3 kHz, delta F 400 Hz, attenuation 40 dB, and at ripple for passband 0.1 dB. You see, we try as far as possible to keep the parameters similar to each other. Okay, so you can easily judge about the results for the, different types. Now, showing key parameters again. Here declaration. Here this time fc1 or fp1 is fs1 minus delta 1, and fc2 is equal to fs2 plus delta 1. Delta p, delta s, the same style. Degree estimation, the same style. F vector having 6 parameters, this time 0, fc1, fs1, fs2, fc2, and half sampling frequency as the last one. What about attenuation? pass, don't pass, and pass. This is band stop. Okay? What about deviation? 1 over delta p, 1 over delta s, 1 over delta p. And the rest is similar. So moving fast. Now, very important take. Change the degree of the filter from lower values up to higher ones and criticize the results. Try both odd and even degrees. Increase, decrease the minimum attenuation in stop band and report the results. Increase, decrease the maximum ripple in passband, and the same for FP, FS, and FS, capital FS. Try two different delta of F for band pass and band stop filters. Okay? What does it mean? Attenuation. Oh, yeah. Try two different attenuation for stop band 1 and 2 in the passband filter. You don't need to keep them the same as each other. Have attenuation 1 for the first area and attenuation 2 for the second area.